In this video, we're going to look at solving quadratic equations in trigonometry. If you haven't seen the videos prior to this, please check those out, as those focus on solving basic trig equations. So if you're happy with that, what we can do is move on and look at quadratic equations. We've seen quadratic equations before. An example might be x squared is equal to 25. So this is a very simple quadratic. We've got an x squared term, which makes it quadratic. And to solve this, we would take the square root of both sides. That would give me plus or minus root 25, and we would have x is equal to plus or minus 5. So two possible solutions to that particular equation. Let's look at a similar example in trig. I'm going to write now cos squared x is equal to 3/4. We're going to solve this equation. Let's say now that x is going to be between 0 and 360 degrees. So I'm just choosing a nice interval to work in. What I'm going to do is exactly the same as what I've done here. I'm going to square root both sides, and that's cos x is going to be equal to plus or minus the square root of 3/4. We can simplify this here, and we can say that cos x is going to be equal to plus or minus the square root of 3/2. Sometimes students forget the plus or minus and simply solve this now for the positive root of 3/2. What I'm going to do at this stage is now split this into two equations and solve both of them. You certainly don't have to do this, but my approach is as follows. I'm not suggesting that you need to draw this. All I'm doing is splitting it up. I'm going to say that cos x is going to be equal to root 3/2, and we're going to solve that in the interval from 0 to 360. And also we're going to look at when cos x is equal to negative root 3/2. At this stage, I'm going to assume that you can solve both of these equations in the interval. If you can't, go back and watch the videos prior to this, as I'm not going to spend a lot of time doing it. This is one of our nice values, so we'd have x is equal to the inverse cosine now of root 3/2. So getting a principal value for x is going to be equal to 30 degrees plus or minus multiples of 360. And by symmetry, it will be 30 back now from 360, which is 330 plus or minus multiples of 360. We're interested in this now from 0 to 360, so we can say that x is going to be equal to 30 degrees, and we're going to have 330 degrees. So they're the solutions that arise from the positive root. At this stage, what we're going to do now is take the inverse cosine, so x is equal to the inverse cosine of negative root 3/2. This is going to give me a principal value for x, and x is going to be equal to, what's that going to give me, 150 degrees plus or minus now 360 n, so multiples of 360. By symmetry, we're going to have 150 back from now the 360, which is going to give me 210 plus or minus multiples of 360 degrees. So from here, we can see that x is going to be equal to 150, and then we've got now 210. So I've got four solutions to this particular equation in the given interval, and I would list them out in ascending order. If you're unsure how I did these, again, just shift mode 3. This is what we looked at in the previous video. The inverse cosine now of negative root 3/2. And that will give us the 150 as a principal value. And then by symmetry, I've simply done 360 minus that answer. Okay, so here are the four solutions. So what we could have done is made the error of just simply taking the positive square root. If we look at this graphically, what we're going to have is the following. So this right here is y is equal to cos squared x. You could have written this, let's just type this in, y is equal to cos, let's just put a bracket rather than 9, cos x, and then we could have squared this. That is the same, it's just we have the notation now with these positive integer powers, but we can put them like so. So it's neither here nor there. But what we can see from 0 to 360, 360 is about there, we've got 1 2, 3, 4 solutions. And these are the solutions that we picked up. We can see that one just there, if I can get it right on the, see if I can, no, there we go, it's somewhere, there we go. So that gives us 30 and 3/4. We're going to have, the next one we saw was 150, which they're 150 3/4. The next one we had was the 210, and then we had finally the 330 when I can get it on, there we go. So that shows us how we can solve it. If we had only solved for the positive root, then we would have only had the solutions just here. So hopefully that gives you an insight of how to deal with this. We might have other types of quadratic equation, but the idea of this video is to look at all of the different scenarios and look at ways in which we can solve them. Okay, let's have a look at some. Well, I'll solve the following equations for x between 0 and 360. So here we got sine squared x is equal to 1/2, and we're looking for x between 0 and 360. So it's exactly the same. I'm going to take the square root of both sides. So all I'm going to write then is that sine x is going to be equal to plus or minus the square root of 1/2, which we can write now as 1/√2. So that's what I have here. This again gives me nice values here. This is one of our special angles, and initially when you're doing these building exercises it will often be the case, such that you're not dealing with nasty numbers. So sine x is equal to positive 1/√2, and sine x is going to be equal to negative 1/√2. With these, we can go ahead and look at symmetry and odd and even functions when you're solving these, but you don't have to. You can just go ahead, find a principal value and go from there. So what we're going to have, principal value, we'll solve this one first. X is going to be equal to the inverse sine to a -1 on your calculator of 1/√2. X is going to be equal to, that's going to give us 45 degrees, plus or minus multiples of 360. By symmetry, we will have 45 back from 180, which will give me 135 plus or minus 360n. Okay, so from here we can see that this is going to yield the two solutions in the given interval, as if I add or subtract multiples of 360, or if you like, change the value of n, we're going to go outside the interval. So we've got 45 degrees and we've got 135 degrees. Okay, at this stage I could just write these out purely based on the fact that sine is an odd function. So if we've got now this negative 1/√2, let's just show exactly what I mean with this. What we could have, what we've just done is solve the positive, and we've got that one and we've got that one. If we go this way, what we're going to have now is that one and that one. But of course we're interested in this from 0 to 360. So x is going to be equal to the inverse sine. So again, we're finding a principal value, as we discussed before, for x. And x is going to be equal to negative 45 plus or minus multiples of 360. And by symmetry, it will be 45 on from negative 180. So that's going to be negative 135 plus or minus multiples of 360. If we have sine of negative x, it's negative sine of x, and that's the odd function if you'd like to use that. So with this one, what we're interested in now are the solutions just here. So all we're going to do on each of these is just simply jump forward by the 360 degrees. So if we do that, what we're going to have then with this particular one, we're going to have 315 degrees, and this one, if I subtract that, what's that going to give me? 225, so x is going to be equal to 225 degrees. So again, I would list these out in ascending order. We would have now 45, 135, 225 and 315. If you're not sure, take your calculator, it's already in degrees mode. Inverse sine now of negative 1/√2, this will give us negative 45 degrees. And that's what we get, and then we would simply add the 360, and that will give us now the 315. And again, you can find the other solution going this way, but we discussed that in previous videos. Right, let's have a look at the next one. Tan squared 2x is equal to 1. So not only do we have a quadratic, but we also have 2x instead of x. So the first thing I'm going to write out is that tan 2x is equal to plus or minus the square root of 1. So at this stage, what we're going to have now are two equations to solve. We're going to have tan 2x is equal to positive 1, and tan 2x is going to be equal, let's just get rid of that bit, tan 2x is equal to negative 1. We've seen how we deal with these multiple angles, so we can write now that tan 2x is equal to positive 1, and then tan 2x is equal to negative 1. Again, we can use the fact that tan is an odd function here, or you can use symmetry, or you can look at it many different ways. So 2x is going to be equal to the inverse tan, so inverse tan of 1. Inverse tan of 1, again, a very nice number. That is going to give us now, on here, positive 45. So 2x is going to be equal to 45 degrees, plus or minus multiples of 180, as we've seen with the tan curve. So x is going to be equal to, dividing through by 2, we're going to have 22.5 plus or minus now multiples of 90 degrees. So we can see on here that x is going to be equal to 22.5. We're going to add 90, which is going to give me 112.5. We're going to add 90, which is going to give me, what's that going to give me? 202.5. Let's just put that on, 202.5. So all I'm doing is simply now adding these multiples on. So 202, let's just check that, 90, 202, what are we going to have now? 292.5, and they now are the solutions in the interval. Can't squeeze another one in as we will go outside. Okay, so let's look at the next one. What we've got then is 2x is equal to the inverse tan now of negative 1. So 2x is going to give us negative 45 plus or minus multiples of 180 degrees. So x is going to be equal to negative 22.5 plus or minus now, what's that going to be, the 90. Remember, we're splitting this by 2, as we saw in the previous video. So what's that going to give me? X is going to be equal to 67.5 if I add a multiple now of 90. We're going to get 157.5 if I add a multiple of 90. We're going to get now 247.5 if I add another 90. And finally, what's that going to give me? 337.5. Hopefully I've been able to add 90 each time. You might say, why can't you add 90? When I'm speaking, for some reason, it's slightly more challenging to add 90 degrees. But there we go. We've got now 8 solutions in that given interval. And again, if we wanted to graph that, we could do. Let's go ahead and do that. So what we've got, let's put it here. So y is equal to tan, and then we're going to have squared. And at this stage, we're going to have 2x. Okay, so what we've got then, y is equal to tan squared 2x, and we wanted to know where this was equal to 1. Now that's where it's equal to 1, and we're interested in this from 0 to 360 degrees. Well, there's 360, and we can see that we've got one solution just here, as you can see, 22.5, and then we've got these subsequent solutions here. We can see that one was for 67.5, and then all of these are simply going to now be multiples of 90 degrees on. And we can see that we've got for 1, 2, 3, 4, 5, 6, 7, 8, as we've just shown. So that's nice and logical, and that's what we have there. Okay, let's move on. Now, the next one is slightly different. We've got 2 sine squared x minus sine x is equal to 1. This can be written as a quadratic equation in the form ax squared plus bx plus c is equal to 0. All I'm going to do is rewrite this, and I'm going to write this now as 2 sine squared x minus sine x minus 1 is equal to 0. Luckily for us, this is all in terms of the trig ratio sine. Sometimes we will get examples of where, like for example, this one just here, we got sine squared and cos. We will need to use an identity to turn that equation into cosine. So if we've got this scenario where we've got a squared term and a single power term, we turn it to the ratio of the single power term using an identity. Fortunately, this one we don't need to. I'm going to go ahead and factor this. You could use the substitution, and I'll show you initially how using a substitution. Let p be equal to the sine of x. If you would like to see it this way, what we have is 2p squared minus p minus 1 is equal to 0. This is going to factor to 2p plus 1, and then we're going to have now p minus 1 is equal to 0. So if you've gone that approach, that is perfectly fine. I generally don't, but I'm more than happy if students prefer to take it away from this. So what I could have written instead is that 2 sine x plus 1 multiplied by sine x minus 1 is equal to 0. And that's a nicely factored quadratic equation. So what we're going to do is say that 2 sine x plus 1 is equal to 0. So let's just check if I expand this out. 2 sine squared x minus 2 sine x plus sine x minus 1. So what we'd have if this was equal to 0 is that sine x would be equal to negative 1/2. If this was equal to 0, we could say sine x was equal to 1. Two different equations, and all we would do is go ahead and solve them. So I'm going to get the table back up, which you certainly don't need to do. If you're in an exam, you can just consider this one and write out the solutions, then consider that one. The reason I introduce this is so you can see that you're dealing with two equations, and it might trigger your mind to say, when I've taken the square root or when I've factored it, have I put my 2 out? So let's deal with the easy one first. That is sine x is equal to 1. I'm just going to write out the answer because this is between 0 and 360. There's only one. If you wanted to, you could draw a sine curve. Now, what we're going to have is something like that. This is our maximum, and that is going to be at 90, 1. And that is where sine x is equal to 1. If you want to, you can go ahead and solve it. I'm just going to write it there. Right, sine x is equal to negative 1/2. So that's the one we're dealing with. So principal value x is equal to the inverse sine of negative 1/2. This is going to give us that x is equal to negative 30 degrees plus or minus multiples of 360. And by symmetry, x is going to be equal to negative 150 plus or minus multiples of 360. So we can see on here that in this particular interval, if we solve these, that's going to give us that x is equal to 330 degrees, and we've got x is going to be equal to 210 degrees. So they're my solutions. Now if you think what I've just done is solved for this point right here where we've got negative 1/2, that's given me now negative 30, and this one has given me negative 150. I've simply jumped now to these two in the interval that we need. So 3 solutions to that equation in the given interval of 0 to 360 degrees. Okay, this one here has already been factored for us, so we don't have to do anything. I say don't have to do anything but solve those 2 equations that come from the factors. Don't go ahead and multiply this back out as the work's done for us. So what we could have here is now that cos x is equal to 1, and then that sine x is equal to 1/2. They're nicely factored, and all we would do is consider these. So again, relatively straightforward equations to solve in the interval here, and if you want, you can just write them out. So if you looked at the cosine curve, where is the cosine curve equal to 1? Let's do that. It's equal to 1 at 0, and it's equal to 1 at 360. If you wanted to take the inverse cosine of 1, you can do. I'm just going to write them out, as we should hopefully be cool with solving these. So x is going to be equal to 0 and 360 degrees. Where is sine equal to 1/2? Well, we've seen this in many different scenarios here. What we've got is 30 and then 150. So I'm just going to write x is equal to 30 degrees and 150 degrees. If you wanted to, I wouldn't do this in an exam, I'd show 4 work-ins, but these are nice values where we get the special angles. Right, okay. This is where things start to get quite interesting. What we've got here is sine squared x, and then cos x. Cos is to the first power. As stated earlier, when we have this scenario, what we're looking to do is turn this into cosine. So I want a quadratic in cosine. We know the identity that sine squared x plus cos squared x will always give us 1. Therefore, what we can do is manipulate this to get a quadratic in cosine. If I had, for example, 4 cos squared x minus 4 sine x minus 1 is equal to 0, I would now turn this into an equation in sine x. I wouldn't go for cosine, and the reason being is because now we don't at this stage have an identity that makes it easy to take that to being a cosine. So what I'm going to do is write this out, and if sine squared x plus cos squared x is equal to 1, we can say that sine squared x is going to be 1 minus cos squared x. And I'm going to be very, very clear in leaving this in my workings for the examiner to see. So this now is not relevant to what we're doing. This is very relevant. So what I'm going to have is 4, instead of sine squared x, 1 minus cos squared x minus the 4 cos x minus 1 is equal to 0. If I multiply this out, what we're going to have is 4 minus 1, which is going to give me 3, minus 4 cos squared x minus 4 cos x, and that is going to be equal to 0. Rewriting this to make it now look a little nicer in the form ax squared plus bx plus c is equal to 0. 4 cos squared x plus 4 cos x, then we're going to have minus 3 is going to be equal to 0. Again, you can at this stage use a substitution if you wish to factor it, rather than dealing with this cosine. I'm not going to do that. I'm just going to go ahead and factor this in terms now of cos. If you wanted, let p be equal to cos squared x, and you would have here 4p squared plus 4p minus 3 is equal to 0. If you see that, that's perfectly fine, as long as you bring back the cosine. What's this going to, 4 times by negative 3 is negative 12. That will give me 6 and 2. I think this is going to factor to 2 cos x, and of course we can check this. 2 cos x plus 3, and then we're going to have now 2, what are we going to have? 2 cos x, and then we're going to have now minus 1. Hopefully that's going to work. Let's just check that. 4 cos squared x minus 2 cos x plus 6 cos x, that works, and then minus 3. Nice. Okay, so if we look at this, this factor right here would give us now that cos x is equal to negative 3 over 2. We like it when this happens because we know that cosine x can never be equal to negative 1.5. We got a maximum at 1, or a maximum of 1, and a minimum now of negative 1. Therefore, it can't be equal to that. So this one right here, we've got now cos x is going to be equal to 1/2, and all of a sudden this has turned out to be very nice for us. So all we would need to do is solve this one equation. If this did, for example, fall between negative and positive 1, then we could solve that one as well. And often this will become, so for example, if that was 3 cos x plus 2, we'd have to solve where cos x is negative 2/3. And that's very realistic, and it will come up in some questions. And it's obviously not going to give us one of our nice values. So on this, x is going to be equal to now 60 degrees. So an x is going to be equal to 300. If cos x is equal to half, x is 60 or 300 degrees. Again, if you want to check those, do look on a calculator. I'm not going to go through the whole process of solving cos x is a half, as it's one of our nice values. Right, okay, let's look at this one. This looks a complete mess. 2 cos of 1/2 x is equal to tan of 1/2 x. At the moment, I've got cosine and tan. Ideally, I want this as one trig ratio, or that I can factor it like that. What I'm going to do is write to the examiner that tan of 1/2 x can be written as an identity now as sine of 1/2 x over cos of 1/2 x, as long as cos of 1/2 x does not equal 0, as we can't have division by 0. So what I've now got is the following. I've got 2 cos of 1/2 x is going to be equal to sine of 1/2 x over now cos of 1/2 x. What I'm going to do at this stage is multiply through by cos of 1/2 x. If we multiply cos of 1/2 x by cos of 1/2 x, what we're going to get is cos squared of 1/2 x. So that is what we have, and that is equal to sine of 1/2 x. Ideally at this stage, this isn't going to factor as it is, so I'm going to use now that cos squared 1/2 x is going to be equal to 1 minus, and we can say sine squared of 1/2 x. So I'm using my identity, and I'd write to the examiner that I know cos squared of 1/2 x plus sine squared of 1/2 x is equal to 1. Therefore, cos squared of 1/2 x is going to be equal to 1 minus sine squared of 1/2 x. This is going to turn this into a quadratic equation in now sine. So what we've got then is 2 lots of now 1 minus sine squared of 1/2 x. That will be equal to sine of 1/2 x. If I multiply this out and just bring everything now to the right hand side, we're going to have minus, what is that going to be, minus there, so we've got negative 2 sine squared of 1/2 x. So if I add that to both sides, we've got 2 sine squared of 1/2 x. Then we've got plus the sine of 1/2 x. And then we're going to have on here now, that's going to be minus 2 is equal to 0. So this is what the quadratic will now look like. So let's just check that. That looks good, and that's what we'd have. We now need to solve this, and that doesn't look like an easy quadratic to deal with. But let's go ahead and look at that. So looking at that, that is not going to factor. If you want at this stage, you can let, and you can write it here, let p be equal to sine of 1/2 x. If we had that, we would have now 2p squared plus p minus 2 is equal to 0. That's not going to factor, so on this you could go ahead and use the quadratic equation, or you could complete the square. It's entirely up to you. The value of a is 2, the value of b is 1, and the value of c is negative 2. I'm just going to complete the square, so dividing through by 2, we got p squared plus 1/2 p minus 1 is equal to 0. Entirely up to you. If you've used the quadratic equation, you're welcome to do that. So we're going to have p plus 1/4 all squared minus 1/16, and then we're going to have minus 16/16, and that's equal to 0. So what we're going to have is p plus 1/4 is going to be equal to plus or minus now the root of 17. I'm assuming that you're fairly comfortable with solving these. So p is going to be equal to negative 1 plus or minus root 17, and that's all over 4. I would suggest that if you don't like completing the square, just go ahead and use a quadratic equation. Right, so if you'd use sine x here, what you would have now had is that sine, or I should say sine of 1/2 x, sine of 1/2 x is going to be equal to negative 1 plus or minus the square root of 17 over 4. Now let's just look at this. Remember, what we've got here now is a value, and we need this to be between negative and positive 1. So if we look now at negative 1 plus now the root 17. Now root 17 is just over 4. So root 17, and that's going to be now over 4, and that gives us now, what's that give us? Okay, so that's 0.78 and so on and so forth. I'm just going to store this in the calculator, and that is going to be shift store A. If we consider now on the next one, let's go ahead. I suppose we should have, let's get that back, -1, so we do -1, and then we do plus now the root of 17 over 4, so that's going to give me, we did negative last time, didn't we? That's going to give me, no we didn't, we did need to do the negatives, didn't we? That's going to give me now -1.28 and so on and so forth. So what we can say then is sine of 1/2 x cannot be equal to -1 minus root 17 over 4. So what we've got then is this equation to deal with. Sine of 1/2 x is going to be equal to -1 plus the root 17 over 4. And that's the value now that I've got in the calculator. Remember, we're doing this now from 0 to 360, so this one is a real toughie. So if I just bring that back, there we go. I should have realised that we did the positive first. So at this stage, we're working in degrees, and what we'll do is take the inverse sine. So shift sine of this value A. What we're going to have then is 51.33. So what we can say at this stage is that 1/2 x is going to be equal to the inverse sine now of -1 plus the root of 17 over 4. So we can say now that 1/2 x is going to be equal to this value right here. So that's going to be 51.3 blah 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 dot dot dot, and then we've got plus or minus multiples of 360 degrees. I'm just going to store this one in, and I don't need that value anymore, so I'm going to store this as A. You could store it as B and the next one as C. I'm just going to make my life slightly easier, and I'm going to say shift store A. What we're now going to get by symmetry, we'll have this value back from 180, so 180 minus that answer, and that gives me 128.668. So we can say 1/2 x is going to be 128. Let's go ahead and look at that. 128.668, 668, blah, 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 plus or minus multiples of 360 degrees. And I'll just store that in as B. So what we're going to have then is shift store B. Okay, I've already got A, there's B. Exactly the same as we did before. What I'm going to do now is say that on this, if we just consider now, we go to the next step and we can say that x is going to be equal to 2 lots now of 51.33, and then we're going to have plus, all the little bits on there, plus now multiplying this by 2, plus or minus 720n. And then for this one, what we're going to have is x is going to be equal to 2 lots of the 128.66 dot dot dot, plus or minus multiples of 720 as we're multiplying through. Okay, so all we're going to get now is the following. We're going to get on here now, if we just go ahead and do that, we'll have 2 times by this one, so multiply that by 2, that's the bottom one sorted. I think we were stipulating that these needed to be done to 1 decimal place. I'll do these ones to 1 decimal place. In the last video we looked at that. X is equal to 257.3 degrees, so that's that one. And then of course we've got A just here, and multiply that by 2, and that's 102.7. So X is going to be equal to 102.7, and that is the other one. So they're the only solutions in the interval. So as you can see with that one, that is really, really quite tough. But hopefully you've seen a technique in which we can solve it with the knowledge we have. Later on, when you learn new identities and so on and so forth, you might want to look at that slightly differently. But essentially that is the process. So if you got that in an exam, as you can see, it's quite a bit of work to be done. Right, let's go on and look at some more. We're asked to solve the following equations for x between 0 and 2 pi. So now we're working with radians. Cos squared x minus sine of pi by 2 minus x is equal to 2. This brings us on to something really quite interesting. If we have now a little right angle triangle, and we'll go ahead and draw that, let's get this right here. Let's say now that what we've got is this angle right here, and let's call this one x. So if we've got x here, we've got a right angle here. This value is going to be now 90 minus x. Okay, so if we look at this right here, and this is one way of doing it. Another way of seeing this is the graphical representation of the sine and the cosine curve being translated. I think it's easier to see this. So let's call this one A, let's call this one B, and let's call this one C. So if I said now cos x, what we've got, cos x is going to be now the adjacent over the hypotenuse, which is A over C. If I look now at sine of 90 minus x, so 90 minus x, that is going to be the opposite over the hypotenuse, which is A over C. Therefore, what we can say at this stage is that cos of x is going to give us now sine, let's write sine rather than a bracket, sine of 90 minus x, and of course we can write that the other way around. So now we can write this as sine of 90 minus x. We could say that sine x is going to be cos of now 90 minus x. Again, if we did sine x here, consider that would be B over C, opposite over hypotenuse. Cosine of 90 minus x is the adjacent over hypotenuse, which is B over C. If you wanted to look at that in terms of a graphical representation, we've got the sine curve like so. The cosine curve is simply now a translation of 90 degrees. So we'd end up with something that looks like that. Let's go ahead and do that. And there we go. It looks something like that. So it's just now a translation of 90 degrees. So what I'm going to do is state that sine of pi by 2. Remember, pi by 2 is 90 degrees. Pi is 180, 2 pi is 360. So what I'm going to write is the following. I'm going to write now that sine of pi by 2 is 90 degrees, minus x, can be written as cos of x. So that's what I'm going to do. Tell the examiner what you're doing. So what we've got here is cos squared x minus cos x, and then I'm going to subtract the 2 from both sides, and minus 2 is going to be equal to 0. At this stage, I'm going to factor. Is that going to factor? So if we do now cos, let's just see if this will do it. So cos x plus 1, and then we're going to have, now what's the next one going to be? Cos x minus 2 is equal to 0. So let's go ahead and check that works. Cos squared x minus 2 cos x plus cos x minus 2. So from this we can see that cos x is going to be equal to negative 1. With this one, cos x would be equal to 2. Now cos x can't be 2. We've seen that cos x has got a maximum of 1, minimum of negative 1. So all we need to do is solve this equation that cos x is equal to negative 1, and we're interested in this between 0 and 2 pi. If I drew the cosine curve between 0 and 2 pi, it comes round like so here. This one is going to be pi by 2, 90 degrees. This one just here is going to be pi, 180 degrees. This is going to be 3 pi by 2, and this is going to be 2 pi. So where is it negative 1? The answer is x is going to be equal to pi radians. If you are unsure, in the calculator, shift mode 4. We're going to do now the inverse cosine of negative 1, and that will give us now pi. We can see that this is symmetric about here, so we don't need any other solutions in that interval. Right, let's look at the next one. Here's a quadratic in tan. This is quite nice because it's relatively straightforward. If I said now here's a quadratic 3p squared plus 5p minus 2 is equal to 0, solve that. That would be perfectly fine, and we could just simply go ahead and solve that. It looks like it's going to factor, so we can go ahead and factor that. So what will that give us? If we look at that, what we're going to have 3p minus 1 and p plus 2. Let's have a go with that. So 3p minus 1. If you're ever unsure, you can use the quadratic equation on these. And then p plus 2, that's equal to 0. Let's just check that. 3p squared plus 6p minus p minus 2. So that works. So what we could do is simply write this now as 3 tan x minus 1 multiplied by tan x plus 2, and that's equal to 0. So again, we've got two equations to solve here. We got this one. If that's set to 0, what we can say is that tan x is equal to 1/3. And then if this one's equal to 0, we can say that tan x is going to be equal to negative 2. So all we're doing is solving each of these equations for tan in the given interval in radians between 0 and 2 pi. So let's go ahead and deal with this one first. So what we can do is write down now that x is equal to tan to the minus 1, but inverse tan, or on your calculator, shift tan. So let's put this in radians, which we already are, shift mode for. I always do it anyway, just to check. If you're unsure, that'll be a little r. If it's d, it's in degrees. So what we'll have then is the inverse tan. So inverse tan of 1/3. This will give us a principal value. So that's going to give me 0.321 radians. So x is going to be equal to 0.321 ... plus or minus multiples of pi. Remember, the tan curve cycles every pi radians, every 180 degrees. So I'm going to give these to three significant figures, these answers. Initially, we said that it would be one decimal place, but I'll do them to three significant figures. So what we'll have then is x is equal to, and we're interested in this between 0 and pi. So I'm going to be able to add one lot of pi. Quite clearly, I can't add two lots or subtract any from here. So what are we going to have? Let's write this down. So that's 0.322. X is going to be equal to 0.322 radians. Then what I'm going to do is add now to this a multiple of pi, shift pi. There we go, 3.46, so 3.46, so 3.46 radians. And I'm just going to put here now 3SF. So I've given most of three significant figures. If this was an exam question, you would, of course, be told the level of accuracy. Okay, let's deal with this one. So x is going to be equal to the inverse tan now of negative 2. Principal value for x, let's go ahead and do that. This is going to give us a negative value. So shift tan, inverse tan of negative 2. Negative 1.107, so negative 1.107 ... plus or minus multiples of pi. So what we can write then, I'm just going to add pi to this and write it down. So if we just add, and you might want to store that answer just in case you made an error, that's going to give us 2.03, so 2.03 radians. I'm now going to add another multiple of pi, because of course I'll keep us within 2 pi radians, so just add now another multiple of pi, and that's going to give us 5.18 to three significant figures. 5.18 radians. So we got four solutions. There are two, there are two. I'd be tempted to list them out in ascending order. You don't have to. But remember, 2 pi is about 6.28. So as soon as we start going outside 6.28, to give you some idea of the magnitude of pi, or the magnitude of 2 pi, we can see quite clearly that that's not going to be the case. And also, if we think logically here, adding more than 1 pi, well, we're adding 2 pi, which is it's almost like saying add multiples of 360. Well, if we have more than one multiple, we're just going to go outside the interval. Right, let's look at this one here. This one's already factored. Sine x multiplied by 2 sine x plus 1 is equal to 0. So from this, we can see sine x is equal to 0. So this one's nice and straightforward. So if we consider now the sine curve from 0 to 2 pi, where is it equal to 0? Well, it's equal to 0, at pi, and at 2 pi. I wouldn't even go through the process of solving this. I'd just do something like that. So x is going to be equal to 0 radians. We're going to have pi radians, and we're going to have 2 pi radians. So that one's sorted. Then the next one, we've got now 2 sine x plus 1 is equal to 0. So sine x is going to be equal to negative 1/2. Principal value, x is going to be equal to the inverse sine of negative 1/2. This is going to give us now a principal value of negative pi by 6 plus or minus multiples of 2 pi. Our next one, x is going to be negative 5 pi by 6 plus or minus multiples of 2 pi. So what we're going to have are these ones right here. So what I'm just doing is solving these. Now if I did the inverse sign of negative 1/2, we would get negative 30, which is negative pi by 6. We would have now pi by 6 on from negative pi, which is negative 5 pi by 6. So at this stage, all I'm going to do is consider these in the interval, and that is going to give me for the first one. If we add 2 pi, that's going to give me that x is equal to 11 pi by 6, and this corresponds to the value just here. So all I've done is essentially move this one on 360 degrees, or 2 pi. If I now do this one, the next one down here is going to be 7 pi by 6. I'm adding 2 pi radians to this. Remember, 2 pi is going to be 12 over 6. 12 over 6 minus 5 over 6 is 7 over 6. So these are our two solutions, and they're what we would call exact solutions. So they're in terms of pi. So if you're asked now to give your answers as exact or multiples of pi, don't write decimal answers, just go ahead and do these. So what we've got then are 0, we've got 7 pi by 6, we've got pi, we've got 11 pi by 6, and we've got 2 pi. Just check that it isn't a strict inequality like so, because if it was that was the case here, then we would omit this answer. And if it was strict at this end, we would omit this answer. I don't think you would get penalised in an exam, but just check what you're doing. So there we go, looking at solving quadratic equations for examples in trig. We've looked at a whole host of different examples. It's just a case of practicing. Do you need to use an identity? If so, which one? Once you've got now a quadratic, you must remember that you're going to possibly have two solutions. It's not always going to be the case. Again, then when you find those, split it up as we did before, if applicable. Like this we did, and then go ahead and solve, and then give your answers like so. So there we go, 47 minutes. I'm starting to get slightly tired, but hopefully that's been of some use.